Hello. Okay. It is my pleasure to introduce the next speaker, Yoshua Bengio. Yoshua is a professor at University of Montreal and has been involved in machine learning research for many decades. His track record as a researcher needs no introduction. We have already seen his name cited in many of the slides in the previous days, and are all aware of his latest prize, the 2019 Turing Award. What I want to highlight in this introduction is Joshua's commitment to education, his students, and his sustained intent on doing good for the world. At least since 2015, when I was there, a large part of Joshua's lab was made up by students originally from developing countries, a lot of them largely self-taught before they went there. And while he could have hired students from many of the top schools, he consistently decided to take risks and bring us to his lab. And perhaps more importantly, he always found the time to be a hands-on and present mentor to his students. Finally, as you will be able to see in his talk, he has continuously ratified his commitment in doing research that is beneficial for the world instead of a few. So without further ado, Yoshua Bengio.
Thank you for the kind words. So let me start. This talk is mostly forward-looking, trying to think with you guys about the next steps for deep learning on the road towards human-level AI. So let me start from very quickly where I got into this field, because I was excited about what I call an amazing hypothesis that there might be a few simple principles like the laws of physics which could explain intelligence. Of course, our intelligence, human intelligence, animal intelligence, and of course allow us to build intelligent machines. And just as a reference now, we take this kind of thing for granted, but in the 80s and 90s, the dominant AI paradigm was that intelligence was just a result of a huge bag of tricks. Okay, so maybe again some perspective on that time when the ruling approaches to AI were based on symbols and rules. The idea that the intelligence is coming from knowledge that is provided by humans. And there was very little in terms of the probabilistic interpretation. There was very little in terms of the ability to handle low-level perception and action. And one of the big problems with the approach in which humans are providing the knowledge, like in regular programming actually, is that a lot of the knowledge we have, which is in our head somehow, isn't accessible to us. It's intuitive knowledge. And that's a huge obstacle for AI. And that's where machine learning comes in as a solution, right? Because that intuitive knowledge can be learned just like babies and children learn that through their experience in the world. Now, one of the questions I'm going to be talking about today is all this recent work with deep learning and machine learning is great, but it still leaves the sort of high-level conscious cognition that classical AI was trying to address out of reach of current methods. But I think we are on that path, and I'll try to explain why and how. So the neural net approach to AI really is starting from the observation that brains are intelligent, and if we can understand the principles behind them, then we can build intelligent machines. The kind of principles that we know work well in the brain and work well in artificial neural nets are things like the synergy of a large number of simple adaptive computational units, the focus on representation that are learned and distributed, meaning that instead of having a symbol like a cat and a dog each have their own symbol, the concept of cat and the concept of dog have a pattern of activation of these artificial neurons. And those patterns can overlap, which allows generalization across these concepts. And this is the central idea of that Jeff Hinton introduced in the early 80s, that has been the main reason why I got into this field in the first place. Another important point of view, which is slightly more modern, but not that much, is to think of machine learning and the intelligence of the systems that we can build with machine learning arising from combining three kinds of things. On the one hand, objective or reward functions. The the thing that the entity is trying to optimize, and then the way that it's optimizing it, the learning rule or the optimizer, and finally a choice of parameterization and architecture which embeds some further constraints and preferences on the solutions that will be found. And this is basically what we call end-to-end learning, and is very, very successful in the last few years. So deep learning has been amazingly successful, but mostly at perception, to some extent at manipulating language and playing games, but you know, a little bit of reasoning, but it's really out of reach still. And so I think that one of the building blocks for going towards this more high-level kind of cognition is attention. This is a thing that in the last few years has been immensely successful. We introduced a particular form of attention called soft content-based attention in 2014, and we used it to produce what ended up being a breakthrough in machine translation. By 2016, it was in Google Translate. And what it does essentially is it allows to focus computation on a few elements at a time. So computation is seen as a sequential process, and at each step, instead of looking at the whole set of pieces of information that at our disposal, we focus on a few at a time. And you can see how this is important in translation. But in recent papers, we've shown how this could open the door to dealing with long-term dependencies in recurrent nets. It's used in differentiable memory access. It allows to, and I'll come back to that probably, to think of neural nets as operating on sets rather than operating on vectors. Of course, these would be still sets of vectors, but now the notion of working on sets, I think, is very important for higher level cognition. And then these attention mechanisms are part of the state of the art in current NLP everywhere. I mean, transformers, self-attention, and I'll argue is an essential component of conscious machines. Another big advance in recent years is the ability not just to do pattern recognition and classification, but also to synthesize new things, to invent, to imagine. And we've made some progress with things like generative adversarial networks, which were introduced in 2014. So all of these images are synthetic. I'm guessing in the summer school you will be seeing or have seen things like this. So I won't spend a lot of time. But the reason I'm interested in this for high-level cognition is because I'm interested in how we imagine things. So what I'm interested in is not just to produce novel images, but to produce new abstract mental pictures that are part of our plans and allow us to take decisions by thinking about how the future might be or what might have happened in the past. Okay, so let's see some of the current limitations of what we have. Maybe on a practical side, sample complexity, the number of examples you need to get good performance on a new task is really too high and much higher than what it seems to be necessary for humans. So this is a central thing, and this is especially important when you do things like transfer learning, or you basically want to quickly adapt to a new distribution, to a new setting. Another maybe less subtle thing, a more subtle thing is that we still mostly use supervised learning in which the high-level concepts, like cat and dog that I was talking about before, are not things that the machine discovers by itself and figures out, but instead we sort of hard code that these are important concepts by using them as labels in supervised learning. So babies discover actually a lot of things even before their parents will put names on these things for them. Another clue that we have to make some fundamental progress is looking at the kind of errors that the state-of-the-art systems make. And when you do that, there are a lot of papers that have been doing this kind of thing. What you see is that those systems have apparently fairly shallow and superficial understanding or narrow understanding of the world around us, even what you would think would be necessary for solving the task, which is why they make these mistakes. And I think all of these questions are related to the goals that my colleagues and I set ourselves at the beginning of the century when we started working on deep learning. The dream was that we could use some sort of unsupervised learning to discover high-level representations that capture the explanatory variables that are behind what we are observing. And although we've made a lot of progress, I think this is still in front of us. Okay, so I think a good way to understand the limitations of what we have achieved and also give us some clues about what's missing is to consider the distinction introduced by psychologists like Kahneman on different kinds of cognitive tasks, which he calls System 1 and System 2. Some people don't like those names, but anyways. So System 1 is basically, I could just call them unconscious processing and conscious processing. So System 1 is the things you do intuitively. In other words, you don't have conscious access to how you do those things. And you don't have conscious access of how you perceive. If you're driving your car in a sort of automatic way, going to your usual place, you don't need to think about it. It's sort of just going automatically. You can talk to someone near you. Current deep learning does these kinds of things quite well. But what current deep learning doesn't do so well, and what classical AI was trying to do, but failed in a way, is the sort of System 2 tasks where the things you do consciously, the things that usually take much more time, involve some kind of logic. Of course, they go through steps that are explicit, sequential. This is what we do when we program. This is also when we speak. A lot of it is connected to our conscious computations. And one of the things I think that helps in current machine learning, one of the directions of research that helps, I think, to bridge that gap to some extent is the work on grounded language learning, where you're not just trying to learn how to manipulate symbols with language, but also associate those symbols with a world model, a model of the environment that captures the semantics of how these concepts are related to each other in a deep way, and not just through the associations of these words in language. So an example of that is some work we've done recently that was presented at the last iClear, but I think it's just the beginning of a series of work. We called it the Baby AI Platform. So it's a more like a reinforcement learning setting with a synthetic environment, a kind of game, if you want, where the agent has to do things that are specified in natural language in a kind of mission, like put the blue key next to the green ball. And it can be very simple as in this image, or it can have lots of rooms and very complex sentences with a compositional language that we have created for being able to express these things. And I think it's time to push further the synergy between reinforcement learning and deep learning. And I'd maybe use a different term than reinforcement learning because we don't always have reinforcement. But I want to use the term agent learning or the agent perspective. And what I think is that although deep learning has been a useful tool for reinforcement learning as a black box for computing things like policies and value functions, there's another way that the synergy can come up where it's more like that agent perspective can inform how we can do better deep learning. So even if at the end of the day, what you want to do is some sort of static task, you might benefit from having trained the system to interact with an environment so that it learns like causal structure, how the world works. It gets to know how the distribution can change due to interventions of agents, and thus learn to be more robust to changes in distribution. And it can build a deeper understanding of the environment through these models. The other interesting aspect, of course, of the agent perspective is from the point of view of learning. Now, it doesn't have to be a passive thing because the agent could choose during its learning to gather knowledge purposely and to thus build in a directed way the kind of representations that it needs to understand the world. One of the papers we wrote a couple of years ago, and there's been several papers in that direction in the last few years, that goes in that direction is about how the agent perspective can help put pressure on the kind of unsupervised representations that we can learn with deep learning, such that the high-level variables, the high-level factors, correspond to objects and their attributes. And one important idea that comes from psychology, the idea of affordances, is that the way we humans represent objects is not by their shape or something like that. It's by how we change those objects by our actions. And so here, the idea in those papers is do something like maximize mutual information between representations of states of the world, like objects, and representations of our intentions or policies, so that there would be a simple relationship between the two. That's what maximizing mutual information means. And at the extreme, you could imagine that the different dimensions in the representation correspond to independently controllable aspects of the world. And of course, this idea of how an agent can influence the world is highly connected to the notion of causality, because causality is basically about that. It's basically about what would happen if an agent were to do something, intervene on a particular aspect of the world. So that's why I got interested in this. And I think this is really important to build actual models of the world where the agent somehow captures how the world ticks, and doesn't necessarily rely only on the sort of superficial clues that may not be stable as you go from one environment to another environment. And why we care about this in machine learning, because in practice, we're rarely in a situation where the test distribution is the same as the training distribution. We want to be able to predict the effect of actions in scenarios that may be very unlikely under the training distribution. And this is something humans are very good at. I think this is an essential component of reasoning, of our intelligence, and of science. Okay, so some of the work we've done in the direction of capturing those high-level dependencies in the abstract space is based on mutual information that I've already mentioned. One of the things about high-level representations is that they may throw away some of the information and the input that doesn't really matter as far as the agent is concerned, as far as the long-term structure of the dependencies in the world are concerned. And so we've experimented with various unsupervised training objectives which don't require reconstruction, which don't require minimizing some sort of reconstruction error, which has been the case for essentially all of the unsupervised learning methods we've had up to now. And I think this is important because when you consider things like log likelihood in pixel space, it puts a lot of pressure on the learner to care about a lot of bits of information that are maybe not relevant, whereas the important bits of information, like maybe just the one bit or the few bits that correspond to some bullet that is being sent by an attacker, those bits of information are super important for what's going to happen next in the scene, and also super important from the point of view of an agent which is going to act in the world. So let me skip that. So this idea that we need to pay attention to just a few important things is something that has been with me for a few years now. And it's something that, it's not just that we want to throw away the details, but which detail we want to throw away at a particular moment is not always the same. So when we are thinking, notice how we focus on just a few aspects of the world, a few aspects of the state of the world. If I'm thinking about what I'm going to have for lunch, I'm only thinking about the food and where it's going to be and so on. If I'm thinking about how I go back home, I'm thinking about just my position. So depending on my goals, depending on the subject of my thoughts, I'm focusing on a few aspects of the world. So that's one aspect. And the other thing is This is not easy to deal with current like likelihood-based methods because we're not going to be making predictions about everything in the world, but just a few selected things. And again, I think that these kind of information theoretical objectives that we started to explore can be very important for that. And then let me again go towards this notion that we are focusing on just a few aspects of the world in our thoughts. So if that's the case, and I'm pretty sure that's the case, and also what that's cognitive neuroscience is observing, then we need a mechanism to select what aspects of the world we're going to be thinking about at the next moment. And attention is of course the thing, right? And it would be very convenient if we can do this with soft attention, because that means we can backdrop through the whole thing and learn where to pay attention. So we don't have to program by hand what to pay attention on. It's going to be dynamic depending on the context, and we're going to learn the mapping from the current state or whatever current information that the machine has to what it wants to focus on. So this is connected to the C word, consciousness. And it's interesting because in our field in AI, we're still kind of very shy about using that word. Whereas that has changed in cognitive neuroscience. So in cognitive neuroscience in the last 15, 20 years, there's been a shift. People are studying consciousness in a serious scientific way, trying to figure out what are the neural correlates of consciousness and thinking about mechanisms that are underlying it. But I don't think they have all the right tools for doing this. Machine learning is the right field to formalize the kind of mathematical structure and computation that may be associated with consciousness. So let's get the magic out of consciousness and just focus on the computations. And so I had a first paper that proposed a way in that direction a couple of years ago called the consciousness prior. And one of the ideas here is when we're going to do representation learning, we should think now of two kinds of high-level states. There's the usual high-level state, which I call the unconscious state, which contains a lot of information about what we've seen in the input, maybe from the past as well, and is represented at the highest level. So it's all of the high-level concepts that may be relevant to the current scene. But then we're going to make a selection of a few aspects of this, a few dimensions of this, into a conscious state. And the conscious state is going to dominate further processing, is going to condition further processing, is going to condition our next actions, is going to condition even our perception. There's lots of interesting examples of this, like the gorilla experiment, where you don't see the gorilla because you're asked to count how many passes the players are making with the ball. And there's a gorilla in the background, and it's very obvious if you were to pay attention to it, but since you're paying attention to something else, you don't see it. So I call it the consciousness prior because I think of this as a constraint or a regularizer on the kind of distribution that the brain might be constructing about the world. Because you're only allowed to consider a few variables at a time, so you're only able to capture dependencies that involve a few variables at a time. But that's only necessary for these high-level variables. We can still capture complex things involving many, many factors in the unconscious part. But I'm talking about the conscious part. So things like a sentence such as, if I drop the ball, it will fall on the ground, involves very few concepts, right? The ball, the ground, and the act of dropping, and so on. And so what's interesting about this is not just that it involves very few variables, but that in spite of this, these statements are very powerful, very strong, in the sense that the probability of this being true is very high, right? So the idea is we can express this notion in a graphical models term with a kind of a sparse graphical representation called a sparse factor graph. So a factor graph is a form of joint distribution in which we write the joint between a bunch of variables, these are the high-level variables, as a product of potential functions, and each potential function is a function of a subset of the set of variables. So that's why I call it a prior, that, that graph has a sparsity constraint, or it tends to be very sparse. All right, so I think now, if you want, is a good time to try questions. I'm not sure if the sound is going to work, but we are kind of in the middle of my presentation, and we could go for a few questions if you want, if the setup works.
Fantastic. Can you hear us?
Yes.
Awesome. So there's a question right here.
Hi, Professor Bengio. So do you know if there's any experiments similar to the basketball with the gorilla, but instead of on humans, if there's any experiments on animals? Because this consciousness prior is a good hypothesis for humans, but do you know if it actually happens on animals as well?
So I don't know about an experiment very similar to the one with the gorilla, but there's lots of evidence that, say, at least other mammals seem to have computations similar to ours in terms of conscious computation. So, I mean, it's very, very obvious in primates. And the way that, so of course, we're still not sure, because the main way that we're studying consciousness is through verbal reporting. Like, we ask a person, what were you thinking about? What did you have in mind? And so on. Did you perceive this? And so the way that the neuroscientists are going through at this is looking at what is happening in your brain that corresponds to you being conscious of a particular thing. And there's a sequence of events happening with a particular timing. In particular, there's a kind of burst of activity in the frontal cortex that then propagates to the back of the brain. That's very, very typical of a signature of you becoming conscious of particular things. And depending on which parts of your, say, visual cortex get turned on by this wave coming back, that identifies the concepts that you're currently paying attention to. So you can see the same things in monkeys, for example. Now, I think there's still a lot of questions about what degree or what kind of consciousness animals have. It's much harder to study them, but this is the approach that the scientists have been following.
Hi, from the Freestone theory that the brain acts like a prediction machine,
Sorry, I don't hear you well. Can you speak closer to the microphone?
Yeah, I'm in the microphone. From the Freestone theory that the brain acts like a prediction machine, you can not only do one prediction, you could do several predictions about what is going on. So at some point, you have to decide which of those predictions is the real world. So what do you think about the role of the body in the emergence of consciousness? Is the body helping us to detect which kind of false prediction it's really valuable or not? Or what do you think about that?
Okay, so there are lots of things in what you've talked about. So the body is clearly related to emotions, and emotions are sort of primitive, fast computations that allow us to react quickly to things that might be dangerous or might require our immediate attention. So usually emotions dominate our consciousness when they are strong. And so, like, if you have a very strong pain, you can't think about anything else. If you're hungry, the same thing. Or if you're fear an extreme danger, then you can't think about anything else. So there's a strong relationship between emotions and consciousness. And of course, emotions involve a feedback loop with your body. I mean, pain is an obvious part of that, but not only. In general, there are theories like from Damasio suggesting that we can associate emotions with the innate need to maintain a sort of homeostasis. In other words, like you're in good shape. You're not deviating too much from the levels that are good for you. And if you do, or if there is a prediction that you might, that's like fear, then you have to react quickly. So yeah, I think that the body is part of it, although I think for me, everything in the brain and the body is just computation, right? I'm a very materialist person, and so I don't see this as fundamentally different. For me, what's important about the body is very different. It's because it's the thing that allows the brain to interact with the world, and so that's a different issue.
Cool. Maybe one more question, and then we proceed with the talk.
What are your thoughts about Richard Sutton's hypothesis of predicting more than reward is useful, and that if you can predict everything, you have solved intelligence?
Yeah, I think prediction is important.
Sorry. For the specific case of reinforcement learning.
But I think the hard part is knowing what to predict, because there are many things you could predict that are useless. And that's one thing that I think is still missing in Rich's research program. I believe the kind of thing that we're discussing here about imagination and how you project yourself into the future to make a plan, for example, might be interesting guides towards learning what to think about that will be useful for understanding the world or getting rewards and whatever is relevant.
Thank you.
All right, so I'm going to continue, and we'll have more time for questions later. So now I'm going to talk about one of the consequences of the consciousness prior is that we are decomposing decomposing the joint distribution into these little pieces, these factors that involve the interaction of very few variables at a time. And we can think of this as another form of disentangling. Like the early form of disentangling we were thinking about in the early 2000s was disentangle the variables, right? So go from pixels to high-level concepts. But really there's another part of the disentangling job which we hadn't thought about, which is the joint distribution between those variables. I don't think that those high-level variables are independent of each other. And unlike many people who, study supposedly disentangling, like cat and dog are not independent. They often come in the same sentence, or fork and knife. They often come in the same sentence. There are some dependencies. So we need to learn those dependencies, and we would like to factor the knowledge that the joint distribution represents in a bunch of recombinable pieces, which you can think of as rules in classical AI. So how do we discover these high-level concepts? How do we separate those dependencies into small pieces of information so that we can more easily reuse those pieces of information, those rules, in a way that facilitates transfer, adaptation, and so on. I think this is connected also to fundamental questions in learning theory. Most of the learning theory we've done in machine learning studies the sort of easy case where the test data is going to come from the same distribution as the training data. So the IID hypothesis, for example. But in practice, this is never true, right? We see this in industrial deployment of machine learning. And so we have to think about what happens if the distribution changes. But the problem with that is, well, if we know nothing about how it changes, then there's nothing we can say from a theoretical perspective. It might change in such a way that it has nothing to do with the old distribution, and then we're stuck. That is like our prediction is just going to suck. So I think we need to think harder, and I'm going to try to suggest some ways that we can make progress in that. But again, we can take inspiration from humans. So one of the things that linguists have been studying is what is called systematic generalization. And what they mean in kind of linguistic generalization, that we can combine known words, known concepts in new ways, but that's not special, but in new ways that have essentially zero probability under our training experience. So like if I tell you a story that is a science fiction story, you can understand the story, you can figure out what's going to be the end of the story given the beginning of the story. So we are able to imagine things that have not happened, will not happen, so long as they are about recombining pieces we know, and we can reason with that. which, by the way, could be useful for a credit assignment to figure out, oh, I should have done this in the past, for example. Another concept that I think, so this is just to say that modularization is important. But the other aspect which touches on the modern ideas in machine learning is meta-learning. So I think meta-learning might come to the rescue here to think about how changes in distribution are things that you can observe in your training data. So if our training data is not considered like just IID samples from a single distribution, but a sequence of changes in distribution, then we might learn how the world changes. And then we can generalize to new changes in distributions. Okay, so that's what meta-learning allows us to do. And I'll talk more about it. Now, I think meta-learning can help us, but I think there's something else that can help us, which connects these two hypotheses, right? So the modularization aspect and the meta-learning aspect. And so in order to be able to say something about changes in distribution, I think we can exploit an idea that comes from the causality world that I discovered hearing Bernard Shopkoff, and you can find in his book with Peters and Jensing, the idea of independent mechanisms. So what is that? The idea that we can explain what is going on in the world through the composition of these mechanisms. So you can think of that like modules that interact with each other. But they're independent, not in the statistical sense, but in the information theoretical sense. So meaning that it's what they do, how they do it, like their parameters, which are independent from what you have in other mechanisms. So knowing about how a mechanism performs something doesn't tell you about how another one does it. And if it does, that means you have the wrong factorization. You should maybe take the thing that they have in common and put it in a different place, in a different mechanism. All right? So the claim is we can separate our understanding of the world into these mechanisms. We can think of computations that are informationally independent of each other. And why is that interesting with respect to this notion of how the world changes? Well, what I'm proposing is that if there exists such a decomposition of knowledge, then we can assume something about how things change in the world. The assumption is essentially that the changes in distribution would be small in that way of representing knowledge. So like only one of the mechanism changes, or very few of them changes when there's a change in distribution. Of course, if everything changes in the world, anyway, there's not much we can do, right? But it's very plausible that there would be just a few things that change, because most of those changes in distribution are due to the actions of agents, like somebody turning off a switch, right? Suddenly things become dark. So there was only one bit that changed. But from the point of view of pixels, it looks like lots of things changed. So if you are in the right space of representation of knowledge, which I think corresponds to these independent mechanisms, then you would have the advantage that those changes are now much more localized. So they're going to be easier to recover from. Okay, so how do we discover these independent mechanisms? So again, we're thinking of our knowledge about the world as the interactions between a set of modules or mechanisms, and they interact maybe sparsely with each other, right? And when something happens, which creates a change in distribution, only a small part of the whole system changes. So maybe just one of the mechanisms. Because an agent is, at one place in space and in time. And so, like, if I do something, the immediate effect is going to be very local. All right. So that's the hypothesis. So we've studied this in a couple of papers now in the last year. And one idea that we've explored is that if having the right factorization of knowledge allows to recover quickly from a change in distribution, then we can use that as a signal to figure out what is the right decomposition of knowledge. We can use the speed of adaptation as a clue that we have the right factorization of knowledge. And because if we don't have the right factorization of knowledge, then we might try to change a lot of the parameters or all of the parameters. In fact, I think that in current standard deep learning, this is what happens. Like all of the weights want to change when there is a change in distribution. And so you get catastrophic forgetting, where you forget about old things, old tasks. You get very slow transfer. You need a lot of data from the new distribution and so on. Yeah, I asked these questions already. So I have an argument which says that if you have this small change hypothesis and you have the right modularization of knowledge, then you can recover quickly from the change because very few parameters are involved. So this connects with learning theory that says that if very few parameters need to be tuned in order to adapt to some distribution, then we don't need a lot of examples. So we've done a bunch of experiments to explore these ideas, but you can see it in this curve where we compare just a simple setting where there's two random variables A and B, and we want to figure out whether the right factorization is A is the cause and B is the effect, so it's P of B given A times P of A, or B is the cause and A is the effect, so it's P of A given B times P of B. And what we see is that the correct causal structure which corresponds to a particular factorization of the joint recovers faster from a change in distribution due to an intervention on the cause. So the blue line converges faster in log likelihood to as new data is presented. So this is a sample complexity curve. Yeah, and I guess I said these things already, but I want to quote Léon Bottou here, where he says, nature does not shuffle environments, we shouldn't. So this is a talk he gave at the last ICML, actually on the work he did with Martin Arjovsky, who was here, and I think is very inspiring, and you should check their paper. So I wanted to mention quickly Metalearning, because if we're going to try to optimize the speed of adaptation, it's sort of an inner loop, outer loop scenario, where the inner loop is the adaptation, and the outer loop optimizes things like how we're going to modularize the joint distribution, what are the cause, which variables the cause, which variables the effect, or potentially other parameters like how do we encode pixels into the causal variables. So I don't have time to go into what it means mathematically to do meta-learning, but it's just optimization inside optimization, which is not a new idea in optimization, of course. Actually, my brother and I introduced in 1991, and Schmidt-Huber had similar ideas at about the same time, coming from the point of view of, well, evolution is sort of an outer loop of optimization, and then individual learning is an inner loop. But where we are now today is thinking about, even in the lifetime of an individual, you should think of this inner loop as adaptation to changes at a fast scale, and the outer loop is sort of slow changing where we're capturing stable properties of the world. So we've used this in that paper I mentioned to figure out whether A was the cause of B, but also how do we compute A and B from lower level observations, so learning an encoder. And more recently, I'm almost done, we've introduced an architecture for recurrent nets, which we call recurrent independent mechanisms, that is not about causality now, but it's more on the modularity side. How do we learn a recurrent net modular structure where the different modules are sparsely talking to each other through using attention mechanisms to dynamically select which module is sending information to which module, and the information that they are sending are not the usual state vectors, but rather objects, so sets of objects, key value pairs, the kind of computation you already found in transformers, for example. So it turns out that this kind of architecture works really well at out of distribution generalization, so like longer sequences than what you've seen during training or larger images that you've seen during training. We've tested this on also reinforcement learning tasks like the Atari suit, and we see that it greatly improves over the LSTM PPO baseline. And so this is my, I guess I'm going to skip this and now talk about a completely different thing. I think that, it's time for AI and machine learning researchers to realize that because our science has gone out of labs, we have a responsibility to speak about how our technology is going to be used in the world. Because there are dangers and concerns with how it's going to be used. It could be used to derail democracy with monitoring and tracking people, killing in targeted ways with killer robots. It could have impacts on jobs. It can be used to manipulate people through advertising and social media. It can reinforce social biases and discrimination. It can increase inequality and power concentration. All of these things are fixable if we give ourselves the right social norms and legal frameworks. But it's not going to happen by sort of magic. And I think we have a responsibility to be part of the discussion about these things. But it starts small. It starts in our neighborhood. Like each of us should ask, what I'm doing in my work, how does it fit with my values? How is this technology that I'm working on going to be used? Who's going to benefit or suffer from it? What kind of impact is there going to be? And so we might choose to work for a company versus another one, or to work for academia versus a company. We might, personally, I don't want to work on military applications. I don't want to work on beating the stock market. I don't want to work on increasing efficiency of advertising or surveillance. I don't want to work on the efficiency of oil and gas industry or the meat industry and so on. But each of us can make different choices, of course. So basically, I want to say it's great to do the research we're doing to build, better machines for the future. But I think at the same time, we can't be blind about how it's going to be used. And we can act both on the negative side to speak about the dangers, but also on the positive side by deploying our skills towards applications of AI that are good for society. On this, I'm going to stop, and thank you very much.
Yoshua, can you hear us? That was timely. For some reason, it disconnected. Can you hear us?
Yes, I hear you.
Awesome. Okay, maybe we have time for a few questions. There's a hand over there. Hey, do you have the microphone? Or
I have the microphone.
okay.
And speak close to the microphone.
Perfect.
Hi. Professor Bengio, do you think to reach human-level intelligence we can still do it with gradient-based optimization, or do you think that with the small change and the consciousness prior that you proposed, then it doesn't matter?
Gradient-based optimization is so successful that I think our first try should be to build systems that can do these high-level cognition things in a way that's optimized by SGD-like things. And I don't see a reason why we couldn't. So, of course, the classical AI was doing discrete computations with symbols, but we now have a lot of tools in our toolbox, using soft attention, using the mechanisms that we use in NLP these days to to learn mostly in a gradient, with backprop. And at some point we may have to take discrete decisions, but we have tools like Gumbel softmax, or we can use in some cases reinforce. So long as the number of points where we use something like reinforce is small, then it still works. I mean, that's why deep-RL works. But if we were to try to optimize everything at the level of individual parameters using pure reinforcement learning, it wouldn't work. Just the variance of the estimator, the gradient estimator, would just kill us.
Okay, thank you.
Hi, Mr. Bengio. I just want to know your thoughts about the idea of AI-generated algorithms. Instead of, because the first shift in AI was instead to hard code the intelligence using neural nets or something other machine learning algorithms to...
Sorry, can you speak closer to the microphone? I didn't...
Yeah.
You're talking about genetic algorithms?
No, AI-generating algorithms.
AI genetic algorithms?
No, AI generating algorithms. The idea by Jeff Clooney. Instead of
generative algorithms.
Generating algorithms.
GANs, you mean?
What do you think about this? Do you think it's a promising approach? Just your thoughts on this.
So you're asking me if I think that generative algorithms, generative like neural nets are important?
I think he said AI generating algorithms.
AI generating algorithms. That described.
You mean like the AI actually produces an algorithm?
Yes.
Yeah, an algorithm for producing AI. An AI environment, something like this. I described, for instance, by Jeff Clooney in his article. I believe it's...
Yeah, I don't think I still understand the question. You're talking about machines that produce AI?
Yeah. Machines are trying to produce AI. Where do you think it's possible? Is a good idea? Something like this?
I mean, at this point, we are the ones designing the learning algorithms. Yes. Maybe will change in the future, but the kinds of algorithms that we're building, I don't think are very good, and for a long time will be very good at designing their own code. So, I mean, for now, I don't think it's something. And humans, by the way, are not very good at coding. It's very painful. So I don't know. I mean, things might change in the future, but before we reach that, I think we need to solve a number of other problems of the kind like reasoning and doing something that combines the advantages of deep learning with distributed representations, along with the ability to reason with recursion and manipulating discrete entities in a soft way.
Okay, thank you.
Good. There's a question here in the front, I think. Yeah. Okay.
Hi. So first of all, great talk. I really liked it. It touched very interesting questions, and my question is twofold. A part is a little more maybe philosophical. The other one is a little more technical. I don't know. So the point is, you've been talking a lot about being robust on one hand to certain stimuli that the system might get and like take it off balance, and whether you should or not update, for example, the system parameters. That's one. So the robustness thing is like very in the background of all what you said, at least in my understanding. And then you also talked about factorization, in some way the acquired knowledge into modules. And I was thinking...
that's, I think, one way to achieve this robustness is to have the right factorization of knowledge.
Okay, right? So my point is, do you think, or have you tried any kind of like regularization that also imposes factorization into the weights, for example? Like low rank or things like that?
No, no. And I don't think it's the right space to factorize knowledge. So I think the right space to factorize knowledge is the high-level representations themselves, right? So it's not at the level of the detailed computation that allows us to do inference or do encoding and whatever. Think about language. Think about how humans explain the world in ways that we write books about. The factorization of knowledge we use is at the level of these high-level concepts that we manipulate with language. It's not at the level of individual weights or weight matrices or something like this.
Okay. Thank you.
Perhaps, Nando wants to ask a question.
Hi, Nando.
It's nice to see on the big screen. You should see yourself.
Closer to the phone.
I
Okay.
want, given the context where we are here, given the societal context, can you say a few words about Canada and Canada's attitude toward allowing the folks here and the folks in Africa at Indaba attending our conferences in Canada?
Yes.
How should Canada...
Thanks, Nando, for asking the
And
question.
in particular, what can we do about it? How
This
can
is
we
interesting. I think governments can say one thing and do another thing. And it happens because a government is a very complicated machine. So our government has been speaking words of inclusion and diversity, being welcoming to immigrants and so on. And in a sense has done a lot of things in that direction. I can witness that as a professor, for example, in the way that we recruit people, and they're putting a lot of pressure on us to try to be consistent with those values. But at the same time, there are parts of the government which seem to be 20 years behind, like the immigration officers. And it's been a struggle in the last couple of years to kind of force that system to change. I'm not sure if we're going to be successful, but I know that like ministers want us to succeed in this, but the sort of lower levels of the administration are very difficult to change. And in a way, it's also because of the way governments, at least in Canada, are set up, so that the higher-level politicians cannot easily influence the low-level decisions. There's a sort of firewall between these things. They're only allowed to like pass laws, right? Not necessarily tell, okay, you can accept that person and not that person or whatever. So it's not easy. But the good thing is this is what is happening with NeurIPS, and the fact that about 30% right now of the African applications to NeurIPS have been rejected, which is very, very high, is forcing the government to reconsider how they're doing things. And so I'm glad this is happening here in Canada, that, forcing this realization. But in reality, it's happening all over the Western world, that Western countries are being very, very harsh in a way that's not told officially, where the acceptance rates of visa queries from developing countries are incredibly low compared to if you're coming from the West, where you basically no questions asked. And the same application, you just change the country where you come from, and in one case it's accepted, and the other it's rejected. So that's one of the reasons why we decided to put iClear in Africa this year and in 2020. And hopefully the whole scientific community needs to continue putting pressure on governments through these kinds of actions, both protesting about the visa rejections, putting conferences in developing countries, and so on, to increase the awareness about these issues. Thanks a lot for asking the question.
Any more questions? There's a question over there as well. Maybe let's do the one from the lady first.
So, hi. So you mentioned that the right way to factorize knowledge is at the level of high-level concepts. So where can we get those from? The high-level concepts.
You have to learn them as well. I mean, like, you have to learn the mapping from low-level perception and low-level action into high-level concepts.
How do we know if we find...
So you can't do it separately.
Okay.
The overall system basically has two components, right? The mapping between low-level stuff and high-level representations on one hand, and the joint distribution between the high-level things, and that, you can't learn them separately. I mean, you could design toy problems where you're given the high-level concepts and you just have to learn the modularization. But if you want a system that's anchored in perception, which is what we all want, then you need to learn both at the same time.
Okay, right, thank you.
In your model of unconsciousness and unconscious representations, and how do you think it relates to the symbol grounding problem, and if you think that language is relevant to this model?
The last sentence I didn't hear. If I think that's what language?
That language understanding is relevant for this model.
Yeah, so it's precisely motivated by the symbol grounding problem and language understanding that I've proposed these kinds of architectures. So I think that you have to jointly learn this mapping from low level to high level, and that's grounding, as well as the dependencies at the high level, just as I said in the previous thing. And language comes in because I believe that there's a simple mapping between the high level representations, the conscious representations, and utterances in natural language. So a sentence is very close to a thought, right? In fact, that's why the way we study consciousness is ask people to report what they're thinking about. And so I think it could go both ways. So in other words, the progress we make with these architectures and learning procedures based on sort of conscious-like processing will help to build better natural language understanding that is grounded in a model of the world. And at the same time, if the agent learns in the presence of language, then it can get clues about what the high-level factors should be from language, because language, you can think of it almost like language like supervised learning. It's giving very strong clues about what the right concepts should be.
Cool. I think maybe we have time for one more question, and we're done. Okay, in there. No, in here. Yeah.
Thanks. I would like to know what about...
Can you speak closer to the microphone, please? Okay, or louder.
Hi. I just wanted to know what happened with learning in babies. You know that they have no language representation, so if there is any approach from computational learning that doesn't use language and try to imitate how babies know when they are almost 1 year old, for example. If there is some research that is working on some kind of representation that is more related on how babies learn.
Yeah, so there's a lot of work that's being done in cognitive science on child development at every age, from newborns to all years of childhood, and I think they can serve as a huge inspiration for what we're trying to do in machine learning, and in particular this kind of research program I've been talking about. So I'm super interested in this. I talk with some of the people who are working on these questions. And we definitely need to have them in our circles. That's one reason why for many years, for example, the NeurIPS and ICLEI organizers have been inviting people from cognitive science, including people studying children, So I think there's a lot we can learn from babies.
So let's thank Yoshua one more time.
Thank you. Thanks for your questions. Bye.